Before we get into the actual hand calculation of the correlation coefficient, it's going to be useful for us to have a brief discussion about moments about the mean. So let me get this on our board for us. Moments about the mean. And just as way of review here, remember when we're talking x bar, that's the mean of a sample. And when we're talking mu, that's the mean of the population. So in these examples, I'm going to be using mu to represent the population. So let's just kind of jump into it here. So the first moment about the mean, and it's really just probably better that we just kind of jump into it, and then you'll get the intuition here as we go along. So the first moment, if we take a raw score, x sub I, and subtract it from the mean, and we're using again mu here to represent the population. What is this? Well, you could go back to the video on variance and standard deviation, and you would, in sums of squares, if you rewatch those videos, you would know that taking a raw score minus the mean is just called a deviation score. So this is a deviation score. So the first moment about the mean is taking the raw score from the mean. It's called the first moment. And what did this look like for us? If we were to sum these deviation scores, if you remember, if we were to sum the x sub I minus the mu scores, and or you divided them by the total number of scores, you would get 0. Why would you get 0? Because you still have a sign. So the raw scores that are above the mean will be positive, and the raw scores that are below the mean will be negative, and the positive deviation scores will cancel out the negative deviation scores. And if that's confusing at all, I would suggest that you go back to the video in the module, it's probably somewhere around module 4 or 5, where we're talking about the variance, standard deviation, and sums of squares. So that's the first moment. Let's jump into the second moment. So the second moment about the mean, and this is going to become very apparent what we're doing here in just a minute, but the second moment about the mean, again working with this kind of x sub I, it's taking the x sub I raw score minus the mean, mu, and squaring it. That's the second moment of the mean. Well, again, if you go back and we'll watch those videos, or you might already know this answer, what is this called? The raw score minus the mean squared is now called the squared deviation score. And that makes sense, right? If the raw score up here, in the first moment, if the raw score right here minus the mean is a deviation score, then the raw score down here in the second moment minus the mean squared is a squared deviation score. And what happens here now? What does this kind of lend itself to for us? Well, if we were to sum the x sub I minus mu scores squared, divide by n, and this would be n minus 1 if we were using x bar up here. This equals what? This equals a variance. Now notice I'm keeping the parameter here. I'm keeping this as the mean as a parameter here, and I'm keeping the standard or the variance here. This should be sigma squared. I'm keeping the variance as a parameter. I'm keeping the mean as a parameter, and they're lowercase Greek letters. So the raw score minus the mean squared divided by n would give us the variance. Okay. So first moment, raw score minus the mean. Second moment, raw score minus the mean squared. You can probably already guess then, we talk about the third moment about the mean. The third moment is going to be the raw score minus mu cubed to the third power. What is this? this was our symmetry. If you remember, go back to the video on skewness and kurtosis. When we cube this, we're now talking about the symmetry of the distribution. That is, aka skewness. And if you remember, we didn't deal with the formula this way, but let me show you the formula this way, and then I'll show you what the formula that was equivalent to what we did. We calculated this as z-scores. It's just kind of easier mathematically to do it that way. If you were calculating skewness, it would be from raw scores. It would be K3 equals n the sum of the x sub I minus x bar cubed, right, divided by n minus 1 times n minus 2. We didn't do this formula right here. This equation was for the raw scores. We calculated the same thing. We called it gamma 1. So this translated into gamma 1, which was the sum of the zi cubed divided by n minus 1. So we transformed these into z-scores and then cubed the z-scores. But it's the same thing, because what is a z-score? A z-score is a raw score minus a mean score divided by the standard deviation. So in this particular case, this is the same thing. So this kind of component right here is kind of the same as this piece right here. Okay? So that's the third moment. Well, if the third moment is cubed and talking about distribution and called skewness, then the fourth moment about the mean is going to be x sub I. I think you're probably getting the gist here now, minus mu, or the mean, to the fourth power. Okay? And what is this going to be defined as? Well, if x cubed skewness and symmetry, then this is our peakedness of the distribution. You remember the leptokurtic, mesocurtic, platykurtic, and this would be kind of aka kurtosis. Now again, I'll show you the long formula here, but it was, if you were to calculate this with raw scores, it's K4, the sum of the xi minus x bar. Let's try to make that a little bit clearer here, what we're doing. X sub I minus x bar to the fourth, multiplied by this weighting coefficient, and now you'll see why we dealt with it as z-scores. I'll show you the z-score equivalent. We took this whole booger right here and just made it the sum of the z-scores to the fourth power divided by n minus 1 minus 3. So this became our equivalent, and just much easier mathematically to deal with this than it is to deal with this one up here. And so those are your 4 moments about the mean. First moment, again to kind of recap, was taking the raw score minus the mean. We call it a deviation score. Second moment, raw score minus the mean squared. That's our squared deviation score. If we sum those and divide by n, that gives us the variance. And then the third moment about the mean is cubing those deviation scores, and that's our skewness. The fourth moment about the mean is taking the deviation score to the fourth power, and that was our peakiness of the distribution. So this is going to give us kind of a foundational base from which to kind of jump into the correlation coefficient. Thanks for watching the video.